let's talk about whether or not a series will diverge or potentially converge. Okay, a little bit of a caveat here. This is a test for divergence, not convergence, and we need to keep that in mind. I know I just basically read a sentence to you, but a lot of the tests that we're going to do that have begun already with geometric and are going to continue with things called the ratio test and direct comparison and those kinds of things, they're going to be tests for convergence. This one's a test of divergence. I can tell using this test if a series diverges. A little bit of review because sometimes we just throw these words around. A series will diverge if, and I'm making one up here, n equals 1 to infinity of 6n. All right? Plug in a 1, you get a 6. Plug in a 2, you get a 12. Plug in a 3, you get an 18. This is an obvious example. You're going to approach infinity, or negative infinity in some cases, not in this case. So this one, excuse me, is going to diverge. All right, let's move on. Which of these series diverge? And then we're going to circle all that apply. Look here, you're going to look at some old notes, and you're going to realize this one is geometric. And I'm going to write a few little notes on the ones that are obvious. This one's going to be geometric. And the common ratio is 1/2. This is the structure of geometric. The n is in the exponent. There's no other n's floating around. And so r is equal to 1/2. And because 1/2 is less than 1, let's go a little further with that, and greater than -1. This one is going to converge. Because it converges, we are not going to circle it. Once we have all the ones circled that need to be circled, we'll start looking for patterns, and then we'll talk about what this all means. All right, the second one. If I wanted to write this out as a series, I totally could have done it here. I just chose not to. Let's plug in a 0. 0 plus 2 over 0 plus 3, that would be 2/3. Plug in a 1, that's going to give me 3/4. And then 4/5. And we're just going to plug in a 0 and a 1 and a 2 and a 3 and a 4. Okay, as I look at these numbers, I realize that I'm going from 2/3 to 3/4 to 4/5 to 5/6. And eventually we're going to get bigger and bigger fractions that are going to approach a value of 1. So you're going to plug in 100. You're going to have 102 over 103. Well, that's really, really close to 1. And you add a whole bunch of numbers together that are really close to 1, and it's going to approach infinity. So this series is not going to converge. It's going to diverge, and so we will circle it. There we go. All right, next one. This is equal to, we'll plug in a 3, and it's 3. Plug in a 4, and it's just 4. Plug in a 5, and it's just 5. This one's getting bigger. 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. It's just going to go forever. This one's also going to diverge. Okay, I added a little bit on these notes. If you have an old version of the notes, then you'll need to put in greater than 0. But in this case, we have a geometric series with very few numbers. Geometric series. And A over B is our common ratio. I think that's worth saying. So this one's going to be geometric. Look at the structure. And the common ratio is A over B. And this little thing tells a lot. So first of all, let's kind of start from the end. B is positive, and A is bigger than B. So because we have a positive number and then a numerator that's bigger than our denominator, then we're going to have a number that's greater than 1. Right? And because of that, this one is going to diverge. So we'll circle it. We'll circle that whole thing, even the extra stuff with the inequalities. Okay, and then this last one. Which of these series diverge? And this is a tricky one, actually, that's going to come up in a later lesson. This one's a pretty important one, actually. And if we plugged in a 1, we'd have 1 over 1 squared, then 1 over 2 squared, then 1 over 3 squared, then 1 over 4 squared, and then we would keep doing that. And we notice that these numbers are getting smaller. Now, I do want to say this, and this is very important. Just because the numbers are getting smaller doesn't mean that we have a convergent series. That's very important to know. But in this case, that will be encountered later, this one does converge. We will not circle it. So for our purposes, I think we can really look at these two and talk about the fact that we know that these three, but these two particularly, are a little more concrete. They are going to diverge because the numbers are getting bigger. In other words, if I grabbed a random piece of paper, no, let's not grab a random piece of paper, let's just write it. If I had the limit as n approaches infinity, I'm just jumping straight to the chase of the whole thing, of this guy right here. Like these numbers are getting bigger and bigger and bigger. Okay, well then let's plug in a bigger number for n and a bigger number for n and a bigger number for n. Well, what's happening? If I plugged in a super large number for n, I would get 1. I told you that already. Like these are approaching 1. Or in this case, the limit as n approaches infinity of, well, this is the explicit formula. This is n, the explicit formula. This is explicit. This is explicit. That's explicit. That's explicit. That is the way to directly get to whatever term you want. And if I plugged in a big number there, well, that's just approaching infinity. So it's pretty big. So if you add up a whole bunch of numbers that are getting towards infinity, getting bigger and bigger, then you're definitely going to diverge. That's what the nth term test says. So given an explicit formula, a sub n for some series, and that's what this is. This is a sub n. That's the formula, the formula, the formula, the formula with a little extra information, and the formula, the explicit formula. If the limit as n approaches infinity is not equal to 0, just like that one wasn't and that one wasn't, and that one wasn't either, because they're getting bigger and bigger. Just a little hard to explain with those, with lack of numbers, but yeah. If they're approaching a number other than 0, they're getting ridiculously big or ridiculously small, or they can do that. They can alternate back and forth, but get further from 0 each time. Then the entire series, whether it starts at 1 or not, is going to diverge, okay? So I do want you to be careful here. It's a very common mistake that people make when they first see these things. They'll look at this and they'll say, okay, well, if the limit does not equal 0, then the series diverges. So if it does equal 0, then it converges. No, we can't make any conclusions whatsoever. So I happen to know, and you will too, that this one converges, not because the numbers are getting smaller. As we move forward, these numbers are approaching 0 indeed. Yes. If you want to get a little technical with it, and let's do the nth term test right now. Let's be like, limit as n approaches infinity of 1 over n squared. That's equal to 0. What does that tell me? Does it tell me it converges? No, I just happen to know that this specific one converges, but ultimately it would tell me it was inconclusive if I didn't know that.